Welcome to Academic Digest class. Subscribe to the channel. Work, energy, and power is our course today. So, work. Let's start with that. So, we say that work is efforts made, efforts made with respect to change in distance. So the efforts made with respect, or the efforts that causes change in distance, and you know that change in distance is displacement. So, and another word for effort is force. So we can say that work, in summary, is product of force and displacement. With respect to the angle of motion. So this is a better way to define work. Now, what do I mean? In physics, the formula for work is given by F cos theta, then times displacement. This is the general formula of work. Now, the one you normally see, which they tell you is F times displacement. Notice I call this displacement, not distance, because work is a scalar quantity. This is vector. This is displacement is also a vector. Vector times vector gives you scalar. But if you say this is distance, distance times vector is vector. So it's always important you note this. You see some textbooks calling this thing distance, then telling you about the direction change. And you will just focus on the distance without remembering they say distance with direction. And distance with direction is displacement. Very important you know this. So I said work is effort made with respect to change in distance. Work is product of force and displacement with respect to the angle of motion. So you see what I mean? We know that the first quadrant starts here 0. Over here is 90. 90 to 180. 180 to 180 to 270. Then 270 to 360. We need to know that is first quadrant, second quadrant, third quadrant, fourth quadrant. And you know that here all of them, all the sine angles are positive. Both sine, cos, theta, tan. Here sine is positive, here tan is positive, here cos is positive. So if we have this in mind, we can put our brain to use. So let's say when the angle is 0, which means when there is no angle, and we know that cos 0 is 1. Cos 0 is 1. So it will be the same thing as saying f cos 0 times s. So f times 1 times s, which will give you fs. So this is where you get that formula you normally use. Fs, force times displacement. So let's say we have a situation where we have, this is 0, 180 now. So it will be f cos 180 times s. And we know that cos 180 is minus 1. Shebi? Yes. So if we do cos 180, you now have f times minus 1 times s. So you have minus f times s, which is minus fs. So what about when we have 90? Okay, let me be sure. So you see it, and you know that look where 180 is, this side. So what about when I have 90 degrees? When I have the displacement, the angle of motion or the direction of motion to be 90 degrees. So that is the displacement. So you see that this will be the same thing as saying F cos 90 times S. So, and cos 90 is 0. Cos 90 is 0. So it will be F times 0 times S. And times 0, anything times 0 is this way. So you see, it's very important to take note of this. So using this, let's try to look at this question. So we have a question. They gave us force in this direction. Then they gave us friction in the friction present. Then they gave us a body of mass. They gave us body of mass. They did not give us the kg, no problem. Then they gave us the displacement to be 0.6 meter. So notice, to solve this question, we can say the force and friction, the total force there will simply be, so F net will simply be applying Newton's third law, forward force minus backward force, that is action force minus reaction force. So that's the total force there. So it will be equals to F net will be equals to 20 minus 10, which is okay, 20 minus 10. But notice that they gave us minus there. They gave us that the friction is minus 10. So it will be 20 minus minus 10, which is going to be the same thing as saying 20 plus 10. So equals to 30. So assuming they just give us 10, that's what, so equals to 30. So why the displacement itself is 0.6. So they say we should find the work done. So we can see that force is going in this direction, and this direction going this way is the first quadrant. If you remember, going this way is first quadrant, so it's 0. So the formula for work that we use is Fs. You see it. So whenever we notice that there is movement in this angle going towards 180, we apply this one. So we can now do is 0.6. So if we now employ the formula, which is work equals to Fs, we are going to have that work is equals to 30 times 0.6. Let's punch that. Our last class, we're doing a lot of calculations from our heads. So 30 times 0.6. So you get W work is equals to 18. And you need to know that the unit of work is joules. So I can write J, I write joules. So when somebody tell you the joules, you tell the person, yes, I am working. Let's go to the next one. Next question says, given a body such that the force is at perpendicular, is at 90 degrees, and the displacement is going towards the 0 degree, that is towards the first quadrant. So the work is at the 0 axis of the first quadrant. That is, the displacement is at the 0 axis of the first quadrant. So you need to always think of work in what direction are you doing it. Why the force, the effort is being put in this direction. So when we put effort in this direction, you can see that what we are going to make use of is this particular formula, this one. Because the angle between the two, this angle now, the angle between the two is 90 degrees. That's the angle between the two. So an F cos 90 is 0. So everything there is going to be 0. There will be no work done there. There will be no work done there. No work will be done, because if we do work equals to force cos theta S displacement. If we come and put 6 cos 90 is 0. So 6 times 0 times 2, everything will give me 0. So there is no work done there. So let's move to the next one. We have force. See the direction of the force. It's at the 0 axis. Then the displacement is in the opposite direction. It's going towards the 180. Are you seeing it? So we can say at this point, we can say that force is at the force there is at 0, while the displacement itself is going in a different direction. So what we can do here is to say, let's solve for force here. If we say F, watch, number 3, F cos 0. This F cos 0 has no displacement. There's no displacement in this direction. Are you seeing it? So F cos 0, no displacement. So it's going to be equals to 8 times cos 0 is 1. 8 times 1. 8 times 1. So which is equals to 8. It's still 8. Now let's look at it in this direction. Since it's going in this way, since this one is going in this way, so if our force now, we have to take it that force is now going, since this is going in this way, the only force acting this way now, since it's horizontal, the only force acting this way will be frictional force. So there is no forward force here, but the frictional force, which is the one that opposes motion. Once you have any horizontal axis, so which opposes it. So the only force, the only work done here is work done by friction. In this case, the only work done in this case is work done by friction. So to calculate the work done by friction, we will simply say Fr. And notice that it's going in this axis, and this axis, according to our quadrants, notice is 180. So it's 180. So the F there is force at 180, F cos 180, then times the displacement there is 3. I seen it. So you see that if we want to do this now, somebody wants to ask me, so how will you know the frictional force, the amount of frictional force there? So remember that once you have, unless stated, once you have a force this way, there's an equal action and reaction are equal and opposite. There's an equal opposing force there, unless maybe due to certain conditions it's not up to. So that means that I will have, watch, I can say this force here, friction, I have 8 equal, but notice that 8 is a -1. And why is it negative? Because it's going in the angle of 180. So if you don't want to do it this way, you can say that since they are in opposite direction, you say 8 cos 180 times 3. And this is going to give me, cos 180 is -1. So times 3. So this should give me -8 times 3. And -8 times 3 should give you -24. So another way to do this, if you don't want to think of it, somebody will want to ask me, why did I not do -8 here? If I do -8, that means there's no need putting cos again. Assuming I wanted to do this thing, assuming I wanted to do it signifying that it's showing negative of the force, I won't have to do cos 180 again. I will just say, since this is -8 times 3, which will give me the same answer. Are you seeing it? So this cos 180 shows me that it's going in opposite direction with the forward, which gives it a minus sign. But if you don't want to do it that way, you can simply say, since it's friction, is -8 times 3, whichever way. Okay, now let's go to this one. They said the force acting on this is due to gravity. Notice that it's going down. The displacement is going down as well. They said find work done. So whenever we are talking about work done on a body, in gravitation, or work done on a body due to gravitation, we employ force. We employ force in that case to be equals to mg. Then the displacement is equals to the height. So which means that over here, what we will simply have, in this case where they gave us this to be 12 Newton, they are supposed to specify the mass, but since it's not given and they give us force, we can just say in this case what we are going to simply use is just F times h. So which is the same thing as saying 12 times 7. That's the work. And 12 times 7 is going to give you 84 joules. So remember that this one that we did here is still joules. So 84 joules. Now, let's move to the next one. They said we have a body, and this body is in such a way that it is being pulled. Notice that it's pulled at 30 degrees. Then the force is 16 Newton. The displacement is this. So this one, we simply remember that the main formula for work is simply work equals to F cos theta times S. Notice I did not do Fs. No, it's simply force at an angle times displacement. So work is equals to, the force there is 16. 16 cos 30. Then the displacement is times 1.76. So let's do it. Cos 30 is 0.8660. So 0.8660 times 16 will give you 13.856. Now times it by 1.76. You get work there to be 24.39 joules. All right, so let's look at number 6. They said how many joules of work, this is a word problem, how many joules of work are done by a bricklayer who lifts 2.5 kg cement block? Notice that this question is like this one, this particular one, but here they gave us the mass. So the formula we use for work done by a body due to gravitation is simply W equals to mgh. Remember that if I have a body that is on an inclined plane, that the work here, let's say this is A, this is B, that the work here that is happening here is mg at an angle which is sine theta. If you remember, x-axis, sine theta. So let's say we have AB, then let's say everything here is h. So we'll have sine theta to be equals to, sine theta is opposite over hypotenuse. So let's say this is the theta. Opposite of this is h. Hypotenuse, the hypotenuse of this is simply A to B, which is mg sine theta. So let me have my AB. Are you seeing it? So that means that if instead of writing this now, I'll simply say that work will now be the same thing as saying AB times mg times h over AB. Remember that this is the same thing as mg sine theta. Work here is mg sine theta. Remember that this is mg sine theta. The work done on this hypotenuse is mg sine theta. So I replaced mg sine theta. Sine theta, I replaced it with h over AB. So when you put this together, you see that it's AB times mgh over AB. And this will cancel this. So work done on vertically is always considered on the vertical axis, the direction, and not the path that it followed. So you need to know that. So for that reason, I'll simply, to solve this question, how many joules of work are done by a bricklayer who lifts 2.5 kg cement block? So this will be the last for today. So I will have work is going to be equals to, work done there is going to be equals to the 2.5 kg, then gravity, which is 9.8. I normally advise my students to use 9.8, then times 7.2. So 2.5 times 9.8 times 7.2. So work done there is going to be 176.4. So work is approximately 176 joules. So thank you, subscribe. Now next class we'll continue from there. We'll do power and energy. Then conservation of work, conservation of energy, conservation of momentum, and the rest.